feel free to interrupt if you feel uncomfortable or if you have questions. I will try to give you at least the main idea behind this work that we put on archive a couple of weeks ago with Alice over there, dealing with critical exponents in the analytical combinatorial. So I'll start with a little bit of background, which I guess will be familiar to most of you. So assume that you have a family of objects. So that's your family of objects that you want to enumerate. And when you want to enumerate them, those objects are classified by their size. That's the size parameter. And usually what you do, if you want to do analytical combinatorics, you form the generating function of this family. So it's a formal power series where in front of x to the n, you put the number of objects of size n, right? For n larger than 0. And then it's been developed in particular by Flageolet and co-authors that when you have recursions or decompositions in the combinatorial setting, then you have functional equations on the function f, so recursion decomposition of the family A. Sometimes that gives you a recurrence relation. And in fine, what you want to have is asymptotics for those guys. And typically what you have is that those asymptotics is a constant, some exponential growth, and then some polynomial correction factor, n to the minus alpha. And this is a one-to-one correspondence with singular behavior of your function f. So I state it a little bit loosely. So it's some constant prime. And here, if the radius of convergence is 1 over, let me put this, rho minus x to the alpha. So it's minus alpha minus 1. So that the sum is minus 1. Okay. So you have a dictionary between recursive decomposition, functional equations, and singular behavior of asymptotic behavior of your objects and singular behavior of the function f. Okay, so this guy here is the important guy in the story because those constant here, the exponential growth and the constant, these are model dependent, meaning that if you change a little bit your family, but with which has the same large-scale structure, let's say, then those will change dramatically, and this one will stay the same. So this guy is the critical exponent, and is the important guy in the story because it dictates the large-scale behavior of your objects if you think of them as taken uniformly at random in your set. Okay, so that's the important guy. I guess if the audience is made of physicists, you agree on that point, right? Okay, so this is the critical exponent. We want to wait. Yes.
Just a question. Do you know any natural example with a critical exponent being irrational? All the ones that occur are rational.
What you mean by natural? So indeed, I will present you two theorems, and in these theorems, the exponent will be -3/2 and -5/2. You have models with critical exponents which are not rational. Let's discuss what you mean by natural or not.
Natural means you start with a counting problem.
Yes, there are examples. Yes, there are examples, but not of the form that I will describe. It's not we.
Meanders.
Okay. Of course, very hard, the hardest possible. Yeah, the meanders, if you want to enumerate, or plane curves also, but if you want to enumerate those combinatorial patterns. To homeomorphism. But the exponent is just conjecture, right?
It's not proved.
It's not proved. It involves a square root of what?
8.
No, it's 100 something.
145.
145.
You can even find transcendental if you look at the backbone exponent.
Backbone exponent of our percolation, yes, but it's not a counting problem. It's what you mean by natural, what you mean by counting. This is really counting. Yes.
Nicolas, you also have worked on problems with irrational exponents.
Yes, a lot, but I was thinking of triangulation, but the recursive triangulation with the square root of 17, but this is not really counting. In some sense, it is self-governing work. No, it's 3/4.
There's also many interesting natural counting problems where the number grows exponentially corresponding to essential singularity. So this will not be touched.
Okay. No, I will not touch upon that. So yes, there are many, but the most natural or baby example will be rational. And the message I want to convey is that you start, the most simple one will be -3/2, and the next class will be -5/2, and we want to establish universality for this -5/2. Then you can go home. Okay, so let's start with the baby example. It's chapter 1, and just to make the joke with Gromov, it's 1/2. It's trees, right? If you want to enumerate, let's say binary trees. So that's your class of object. Plain binary trees. It's an object like that. The size, say, is the number of vertices. So n is the number of vertices. Then the recursive decomposition is clear. A binary tree is either just a vertex, or it's a vertex to which you attach 2 plane of binary trees. And so your equation is f of x is x plus x squared of x. Right? So recursive decomposition translated in functional equation for f. And from this, so that's a very simple example, you can use exact enumeration, like Lagrange inversion, for example, to deduce that actually the number of plain binary trees is asymptotic to some constant, some rho to the -n, rho is less than 1, and here n to the -3/2. Hence the joke. But that's really more general. And so this can be deduced by exact enumeration, or you do just a singular development of f near its singularity, and you see that there is a square root singularity of that form, square root, so you get n to the -3/2. And this has been generalized a lot by Drmota, Lale, and Woods in the 90s. What they prove is that if you have even a multi-type version of this enumeration, so it's a multi-type trees, but let me emphasize that it is finitely many types, so finitely many type trees. So if you have finitely many type trees, when you want to enumerate them, then you will enumerate them according to their type. So imagine that the type is I between 1 and k. So you will have generative function depending on the type. And this will be some x for the first vertex. And then you have some polynomial of, okay, let me put the x here, polynomial of the other type trees. The type is the balance. No, not necessarily. Could be just think of the color of the vertex. Okay, and so you have many equations like that. So f1, you have some polynomial q1 up to fk of x is use a model, you know that there is this general theorem, you know that you will land on the -3/2, but even you have tools, you have techniques, you have algorithm that enables you to compute everything there. So the floor is cleaned.
Just a very
Yes.
naive question. I mean, these results sounds very surprising, no?
Well,
No, in a sense that is a very general result, and it's quite
yes,
impressive.
but if you look at this very carefully, this system is enumeration of multi-type trees, right? So if you think with probabilistic eyes, this is a multi-type Galton-Watson tree with finitely many types. And when you believe in universality, they should behave the same as monotype tree in the large scale limit. And so the same exponent. But yes,
Thank you.
it's true. Before having proved this theorem, that might be surprising. Afterwards, it is not.
Okay, fantastic.
So you will be surprised by the next result then. Yes? So we?
Yeah. What is not surprising, because these are systems of polynomial equations,
Yes.
anything in algebraic geometry has rational.
Yes, but why 3/2?
That's a different question.
But that's the theorem. Yes. Okay. Exactly. That's the point. This is always algebraic. What I'm going to describe, I will tell you. Okay. Let me enter the details. Chapter 2, half maps. So now let's try to enumerate something which is a little bit more complicated than the trees, which are maps. So I will think of triangulation, which are planar maps made of gluing of triangles, but you may have stuff like that. This is a triangle, up, 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 and je vais y arriver, 1, 2, 1, you, up. Is this a triangulation? Yes. That's a triangulation. I want to enumerate those objects. So my set of objects is plane triangulations. Plane triangulation with say n edges, and I have a rooted edge just to have my root somewhere. Okay, and I form my generating function as the same, like above. Then it's not clear what kind of recursive decomposition you can. Yes.
What about the place including infinity? Does that come? You need that to be a triangle.
1, 2, 3. Okay. 1, 2, 3. Good. Merci. Okay, there are no clear recursive decomposition involving only plane triangulation with n edges. And then the trick is to introduce a more general model. So your set of triangulation, let's say T, which I divide by triangulation according to the size, then actually I will divide this set according to another parameter, let's say P. So N is the size, and P will be the perimeter. What is the perimeter? Let me remove that edge. Now it's the degree of the external face. And the external face, let me put it an edge like that, just to emphasize that it might not be simple. You may have cut points. So P is the degree of the external face. Actually, it's a more complicated problem because now you want to enumerate according to size and perimeter. So what you do now, you form the generating function where you count size and perimeter. So x to the n, y to the p, sub according to this. But now it's a more complicated problem, but you have recursions. So let me just very quickly, if you have never seen that, it's quite complicated to follow. And if you know, then you know by heart. So the decomposition is when you have a triangulation like that, you look at the root edge and you remove the root edge. So either it's the empty triangulation, let's say with one vertex, or it's a triangulation made of two parts which are disconnected if you remove the root edge, or it is a triangulation here made of an edge that connects the same part. That is, if I remove this root edge, this remains connected, whereas this is disconnected. Okay, So if you transfer this into the geometric function, then quickly, I speak under the control of many people in the room, which know that much better than me. So what is this? The perimeter is 0, so y to the 0, and I get just one x. Here, the perimeter, so what do I have? I have f of x, y squared for those two parts, and I just need to add y squared because the perimeter has increased by 2. And here, what do I have? I decrease my perimeter by 1, so it's 1 y, f of y of s. Not quite, because here this triangulation is not unconstrained. The constraint is that it must have a perimeter at least 2. So you have this slight modification. You just want to remove those triangulations which have perimeter 1 and the perimeter 0, but this we know what it is from the equation. Okay, that may seem very simple change, but that actually is quite a change. And to solve those equations, it's not very easy. So what we see here, let me write it there.
Don't you use the explicit solution for those two? You can't compute those two directly.
So yes. Okay, let me. So there are techniques that have been developed by many smart people. So let me write the form of the equation first. So the form of the equation is you have this f of xy is some positive polynomial of x, y, and here you've got the function f, but you also have the first difference of f. What is the first difference of f? It's f of x minus the first guy, and the 0, let's put it under the carpet, divided by y. So I remove the coefficient in y and I divide by y. It's the first difference. So it's of that form, right? And so people like Tutt, Brown, Bousquet-Melou, Jehan, then develop techniques to solve those equations. And in particular, the take-home message is if you encounter such an equation in your life, there are techniques, algorithms that you know from Bousquet-Melou, Jehan that you can implement that will give you a solution. What do I mean by solution? Then in the end, you have that the coefficient in front of y to the 1 f of x. So that's just a function of f, f of x just with a 1, which is almost nothing else than the original problem you wanted to solve, enumeration of triangulation just without a boundary. Then this guy is algebraic. What does that mean? That means that you have some explicit polynomial in x and in f1 that solves this equation P. And the P is explicit. Explicit, algorithmically computable, and so it's amenable to singularity analysis. You can, so it's algebraic, you can do a Puiseux's expansion. And so you can get that clearly my number an will be some constant rho to the minus n to the minus some alpha. And this alpha, as you said, will be rational because it's a critical exponent of an algebraic generating function, right? Okay?
You emphasized in the previous case that the polynomial was positive. Is there?
Yes, positive. For the Bousquet-Melou Jehan technique, actually, it's not to implement the algorithm. It's not necessary that it is positive. For what I'm going to say afterwards, it is very important. So it's a positive polynomial. Yes. It's really a counting problem. Yes.
I just want to verify because I've not seen that notation before, but you really say
this is
square brackets.
You look at everything that starts with y to the 1 in the series.
So you take the derivative.
Voilà.
Y equals 0.
Yes. Okay, so in the end, for any specific problem, you can have an asymptotic expansion like that. What was puzzling is that this guy is always 5/2 in any model that we encountered. There are many models of maps, tamarin intervals, fighting fish, many problems of that form. And always this 5/2 pops up. Always. Sorry. Yes.
When you say F1 is the same as Fx, naively I saw that F1 was a derivative of
so
x of
F1
f at y equals 0.
Is a triangulation that starts with a loop like that, because it has a perimeter 1, the external perimeter 1. But any triangulation with a root can be transformed. So here you go to transform your root. You can do a root transformation like that, and you put your root like this up. And now you transform your initial triangulation into a triangulation with a perimeter of 1. And so that's why I said it's just if you can enumerate triangulation of the sphere with the perimeter 1 on the right of your root edge, then you are able to enumerate triangulations. That's what I said. Okay, and so let me tell you the state of the art. Yes, wait, yeah. Sure.
In this theorem you mentioned,
Bousquet-Melou, yes.
If you looked at the coefficient of y square, is it also algebraic?
Yes. Yes. Once you got this one,
Same exponent.
look. Once you have this one in your hands, this equation becomes very simple. If I give you this function, this is just a quadratic equation in f that you can solve. So once you get this one, it's done. Okay? So the theorem of Bousquet-Melou tells you that this guy is algebraic, that their algorithm will give you an explicit polynomial, but whose complexity increases with the model, of course. Yes, oui?
I think the setting of Pascal is a bit more general because you can take higher powers of the differential operator.
Coming to that.
We will come to that.
Coming to that. So now let's generalize a bit this equation and let's take higher powers. So I will just put an x here just to say that x will be the size parameter. So imagine I have an equation like that involving y, involving f, the first difference of f, the second difference of f, and so on up to finite difference of f. So what is fk? It's the same thing, but I remove the coefficient of y squared, y cubed up to yk, and I divide by y to the k. Okay, so this guy is f minus first y to the I coefficient up to k divided by y to the k. Okay? And I assume that this guy is positive, and I assume that I have some aperiodicity, which I will not describe. It's something technical that holds in any reasonable context. Okay, their theorem of Bousquet-Melou, as Jeremy said, tells you that with this setting, in this setting, then always f will be algebraic. So I'm able to singularity analysis. And then there is a theorem by Drmota, Noy, and you in 2022, telling you that when k, I also assume a nonlinear. I assume that my q is nonlinear. When k is equal to 1, so if I have only one difference here, equation of that form, then always alpha is 5/2. So there is this universality of the critical exponent when I consider such equation with first difference only. So this has been revisited last year by Schaeffer and Duki and Schaeffer. They gave an bijective interpretation of that fact. So the key there is that when you perform the Bousquet-Melou algorithm, there is a trick for k is equal to 1, there is a slight, not a slight, a very elegant and tricky change of variable that transforms your system into a system of that form up there, and from which you can then say it's 5/2. So that's a trick plus also heavy analytic combinatorics after that. The bijective trick, I will not describe it, but you can see it afterwards as a reinterpretation of that trick. And then last year, in 2023, the same Drmota and Eva Maria Hainzl, they prove also that alpha is 5/2 in the case k is equal to 2 plus, I must say, non-obvious conditions. They say, okay, I suppose that something is not 0, but this something you have to compute in any example. So it's not a universal result. Okay, and this one is also a heavy. It's analytic combinatorics. It's a tour de force, really. So now let's state the result.
Wait, do you have just an intuitive explanation why you go from 3/2 in the previous case to 5/2? By this approach.
By this approach, it's a kind of like the Schaeffer bijection, transform your maps into simply generated trees. So you get from 5/2 to simply generated trees, which are 3/2 enumerated by 3/2 in the end. So it's a pointing argument.
Okay, so it's a derivative.
Voilà. The change of variable uses the derivative of the f. So it's a pointing argument, and in the end, the pointed maps turns out to be enumerated by multi-type trees, and so. Okay, so the theorem. With Alice is that for any k, under the obvious so positivity assumption plus aperiodicity plus non-linearity, then alpha is 5/2 always. So you can solve with Bousquet-Melou-Géan techniques, but you will land on 5/2. No, it cannot. No, cannot be. It is okay. In the aperiodicity, I have some growth condition as well. It can grow. I will describe that on the drawing. It cannot be 3/2. Okay, so before describing some element of the proof, let me tell you that our proof is not at all analytic combinatorics. It's probabilistic. We use the fact that we know that there is some exponent, and then we use some probability to say, oh, this exponent must be 5/2. So we build upon this, but we do no calculation at all. No analytic combinatorics calculation. Okay, questions? How much time do we have left? Okay, good.
Is there conformal invariance lying in the background?
No, not conformal invariance, but universality for the tree structure that will appear. So this 3/2 in this setting, the 3/2 is related to the fact that any multi-type, finitely many multi-type simply generated tree like that, when it's large, look like a Brownian CRT, a branch polymer. The 3/2 here is characteristic of branch polymer phase. And here, the 5/2 will tell you that the trees that you have not seen yet, the trees that are behind the scenes for this equation, they will be in the different universality class, which is the Brownian growth-fragmentation tree that I will probably describe if time permits. Okay? All right, so let's enter a little bit of detail. So first, we will use some tree model. So we will say that those equations, okay, so the name of those equations, they are catalytic equations, positive catalytic equation. Why? Because the y, the parameter y, is seen as a parameter that you add to your system to solve the thing and then to remove in the end, like a catalytic product that you see in chemistry. Okay. So 3 elements of proof. So first, I will tell you what is the generic model that those equations enumerate. So for this, I need to describe a little bit of parking on trees. So what do you have? You have a model of plane tree, okay? And for each vertex of your tree, you will have some cars, some number. It's just a positive, non-negative integer attached to each vertex, which is just a number of cars arriving on this vertex. Okay, so these are cars arriving on the vertices. Then, for each edge, you have also a non-negative integer, which are parking spots. Okay, for each edge, you have a number of parking spots. Okay. Voila. And then you will assume that you will do the parking as if you go to the supermarket and you park. What do I mean? Each car arrives on its vertex and goes down towards the root of the tree, trying to park on these parking spots as soon as possible. Let me put one more here. Okay, so the cars go down and they park on parking spot as soon as possible. If they cannot park, then they just exit the tree if it's not possible. Okay? You may say, oh, but in which order do you park the car? This one first, this one first? Actually, it does not matter. There is an abelian property of the model that tells you that the resulting configuration in the end does not depend on the order in which you park the cars. Okay? So you park, don't worry, we will do an example, it's prepared. You park the cars in whatever order,
Cars enter at leaves or everywhere?
On vertices. Look here, they can arrive in the backbone as well. Okay, but we will take care of a very specific configuration. Then we will restrict to those configurations where every parking spot in the end will contain one car. So we will restrict to fully parked trees, meaning that after the process, after parking, all spots are taken. For example, it's not the case in this example if I were to put another parking spot here, because this one would be taken by the red car here, but this one would be free. Okay, so let's do it here. So on the left-hand side, I have such a configuration of a tree with car arrivals and parking spots. And on the right-hand side, I will write the resulting configuration. And for each vertex, I will record the number of cars that have exited this particular vertex. So it's the flux of car going down from this particular vertex. So for this one, for example, the flux of car is just 1, because one car went down. The flux of this one is 3, right? Because 3 cars went down here. But those 3 cars, one will park here, okay? So I have 2 cars coming from the right-hand side and 1 car coming from the left-hand side. So in the end, I have 3 cars visiting that vertex, right? Let's do this one. This one, I have 3 cars visiting this vertex. Those 3 cars, 2 will park, so 1 will come here. The 3 cars coming out from this vertex, 2 will park, so 1 is coming here, and 0 here. 2 plus 2 is 4.
1 plus
1 plus 1 is 2.
1 plus 1 is 2. Merci. Just for you. Merci. So the paper is wrong. So 2, 1 plus 1 is 2, the same 2 as this 4. 2, 2 plus 2 plus 2, that's 6. This is a 0. Hola. Okay, 0 plus 2, 2 minus 1 is 1, plus this 2 is 3. C'est bon? Yes? No? 5?
On the right front, you have 2, and then it should be 1, I think. Because
2, 1 and 2, 5. Good. This one was on purpose.
No?
No? It's 6?
Two coming from the right.
Ah, wait. Because there was 1 coming down, like Father Santa. From the tree. Okay, this is 0. 7 and 5. Okay? So on the right-hand side, I have a multi-type tree, and the type is just an integer on each vertex. Okay? So now what I will do is I will try to enumerate those configurations which are fully packed. And to enumerate them, I will put a weight. So I have been given a weight function. What is a weight function? A weight function is just a function that tells you if I give you the local behavior on a particular vertex, I give a weight to this thing. So a local weight function is a function on vertices. I give you the valency, the number of legs, K. I give you the number of cars arriving here, V cars, V like voiture. I give you the valency, and I give you the number of parking spots, S1, spot 1, spot 2, blah, 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 to spot K, and that gives you a number. Okay, so for each local configuration around a vertex, I give you a number. And now I will form my generating function, f of x, y. I will sum over all fully packed trees, I insist. I will count x to the size of the tree, number of vertices. I will count y to the number of outgoing cars. So the number of outgoing cars here is 5 in this case. So that's outgoing cars. And then I will take the product of all vertices of W log of the local configuration around the vertex. Okay? So that's my f of xy. And I claim that any equation of that form can be interpreted as such a generated function. So I will just do one direction. The other one is almost as obvious. Imagine I want to describe what is the recursive decomposition of a fully packed tree, right? So a fully packed tree, imagine I start with some, do I want this? Okay, I want this. So I want that my outgoing flux is P. And let's assume, for example, that my P splits into this. and I have S1. Let me put 2 ones. Assume that my P splits into S1 spot here, S2 spot here, and V cars arriving here. So what kind of fully packed tree must I put there and there so that if I glue on this pattern, I get a fully packed tree with the flux of P? So let me say that the flux here is P1, but the flux here is P2. So what should I have? I should have P1 cars minus S1 plus P2 cars minus the S2 that will park there, plus the V cars going inside should be equal to P. But I should have the indicator that P1 is larger than S1 and that P2 is larger than S2. Right? And so if you are accustomed to this equation, the fact that P1 is larger than S1, that means that actually here you are taking the S1 F difference. You are plugging an F which must have a flux which is larger than S1. So here you are considering the function which is the S1 difference. So you sum over all such decomposition and you get indeed an equation of that form. And vice versa, if you expand this, then you look at this and you find a local weight which satisfies it. Okay? All right. So now that you have your model of trees at hand, let me tell you how we will find this exponent 5/2. Good. Questions? No? Okay. So next step is to introduce the so-called partition functions, which are just numbers. So I will introduce WP of a little x, but this little x will disappear soon. It's just an x which is fixed. I will soon fix it. So W of P is just the coefficient in front of y to the P in f of xy. So in this sum, I sum only on fully packed trees which have outgoing flux P. Yes?
Okay, maybe I have a question. What happens if you relax the condition of being fully packed in Euro for vacant?
See, if you forget this, then you are enumerating just simply generated trees actually. Because
possibly with an infinite number of types.
No, if you just want to enumerate this and you record the size parameter, if you have no condition on the, you enumerate simply generated trees 3/2. It's really the fully packed condition that changes the exponent.
Okay, and in terms of equations, it means that instead of you don't have difference anymore. It's
Voilà,
it's
exactly, because here, yes, you remove the indicator, you don't have the difference anymore, and you're back to the initial Drmota, Hainzl. Okay, so this number can be used to define a probabilistic model. So what is my probabilistic model? It's a law that I will denote by PP. It's a law on structures on fully packed trees with flux P, just obtained by normalizing this measure, obtained by normalizing. Of course, I have chosen X so that this guy is finite to be able to do this. So now the first idea is to say, oh, but this law PP is nothing but a multi-type Galton-Watson process, but with types in 0, 1, 2, 3, blah, 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 blah. It's the guy that you see on the right-hand side. If I tell you I start from 5, then I will have a multi-type Galton-Watson tree starting from label 5. So just to convince you of that, let me compute for you what is the probability that I see a particular splitting at the root. Okay, so if I'm sitting at the root and if I have P, what is the probability that I see P1, P2, and that I have S1 spot here, S2 spots here, and V? What is the probability under P of that? Double bar here, just not to confuse with the W log. And it's plain. If you want to have this, you put anything here which has flux P1, anything here which has flux P2, you multiply by the local weights of this pattern, S1, S2, and V car incoming, and you divide by WP because you were normalizing by the WP. And of course, here you put all the indicators that makes the thing work. That is P1 is larger than S1, P2 is larger than S2, and P1 minus S1 plus P2 minus S2 plus V is equal to P. Okay? But you see clearly in this formula that if I condition on this, that the tree here is just sampled according to the P1 measure once I normalize. Okay. Okay. Good. So it's a very good Galton-Watson, multi-type Galton-Watson tree. And it turns out that's the advertisement minute, that's the ad. It turns out that it's been a couple of years that we have developed a framework to deal with those multi-type trees with Armand Riera and Jean Bertoin. And we know what are the possible scaling limits of those trees, but I will not use it. But the intuition somehow comes from there. Okay, so now what I will look at is the locally largest exploration. What is this guy? The locally largest exploration is, you imagine your tree that starts from this label P, and I will follow just one branch because I want to find a random walk. To find a random walk, I better have something which is one-dimensional. And so what is the locally largest exploration? You start at the root, and each time you see a splitting, you select the child which has the largest label. You see some splitting, you select your child which has the largest label. You see a splitting, select the child which has the largest label. Ah, there is a tie, choose randomly, this one, and then this one. Okay, so the locally largest exploration, it's the locally largest. These two might be smaller than some other guy here. It's just locally largest. So under PP, the locally largest exploration is just the branch that starts from the root. So up, it starts from the root with P. I will denote that by S0. Then you've got label S1 and R. And you've got on the side some trees that have been left over with some labels here that I will then denote by P1. That's P1 of J. And those parameters are P2 of J. Ah, yes, I use the word perimeter for this label. It comes from the map interpretation. Okay, so that's the locally largest exploration. It's just a process S together with some integers that are left over on the side. Okay, then I will introduce for you an ideal model of locally largest exploration. For that, I need just a little background. Remember, what are those WP of X? Remember, this is just Y to the P in F of XY. And let me think of X0 as being fixed, and I removed from the notation. It's a parameter that has been fixed. Now look at the equation here. If I fix X0 and remove from notation, these guys are actually, now if you remove x0, these guys are actually just a rational function of the f. It's just f minus something depending on y with some coefficient of x, but which are constant now because x has been fixed. So it's just an equation of that form in the end, up to multiply by some high power of y. So it is an algebraic equation. So for each x, f of y is algebraic. So since f of y is algebraic, I know that I can do some analytic combinatorics and know that this WP is asymptotic to some constant, some exponential factor, and some exponent beta, which is actually not known, but rational a priori, right? But I know that I have such an expansion. Okay. Rational but positive. It has to be. Okay, so if you look at this now, and if you go back to this locally largest exploration and think of your starting label, P as being very, 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 very large. Imagine you start from P almost infinity. And you look at all the possible splittings. So I have P1, P2, P3. Now you say, oh, but P1 plus P2 plus P3 minus some number plus some V must be equal to P. But P is very, very large. That means that at least one of these three guys must be very, very large. What is the most likely?
One is very large.
Just one, because if two are large, if this one is of order P, or P over 2, and this one is over P over 2, then okay. Then if you compute the probability with this formula, over there, WP1, WP2 divided by WP, all exponential factor cancels, and you get roughly P1 to the minus beta, P2 to the minus beta divided by P to the minus beta. So if P1 and P2 are of order P, you just cancel one of these P to the beta and one remains. So actually the most likely scenario under PP, it's that only one of those three is huge. Think of this one. And let me write it P plus Q. And I think of P as being very, very large, while Q is fixed. It's a big O of 1. And now let's compute what is the probability that I see such a splitting. Well, it's written over there. It's WP1, WP2, and WP plus Q times the local weight and divided by WP. What?
We may have 5 minutes left.
Yeah, that will do the job. So now when P goes to infinity, using the asymptotic here, you see that those two we cancel and we'll just give a factor rho to the minus Q. Okay? So then we introduce a measure that you think of being the evolution of the locally largest fragment when P is very, very, very large. So you define a measure, nu infinity, on splittings of, you imagine that this guy is almost infinity, and you ask what is the probability that this almost infinity splits into P1, P2, and this star plus Q, having S1 spot here, S2 spot here, S3 spot here, and V. And up, that's this formula. Okay, you introduce this. This is the limit of the probability of splittings when you start from a very large P. Okay? So now you use this limiting measure. So lemma 1, this is a probability measure. Because priori, this might be a sub-probability measure, but it is actually a probability measure. And the idea is just what we said. The most likely scenario is that actually only one is very large. Once you have this, you emulate this locally largest fragment and you make an ideal model. So what is the ideal model? The ideal model is almost a random walk model, meaning that you imagine that you have Qi, this Q is this guy here, and Pij, those guys here, and that guys for all I, these are IID sampled according to this measure. You see what is this Q? This Q is the difference of the labels of the largest guy, this Q, and the Pi are the labels that you put on the side, and you sample them IID according to this measure. Okay? So if you sample them I should not have removed that, but too late. If you sample them IID, you create an ideal model, which I did not use low, I did not simple random walk. And this simple random walk model started from P. It's just obtained by you start P here, which is S0, and S1, S2, and so on. This is just obtained by summing those guys. This is S0 plus the Q1. This is just S1 plus the Q2, so on and so forth. So you sum just those increments. And the guys that you will put on the sides are those PI. And this model goes forever. Of course, it may be the case that those S2 become negative because you sum increments, and actually they will become negative. Okay, so now the picture is like that. This locally largest exploration, if you picture the S, it's something that does something like that. And if you picture the PIs that you put on the side, these are numbers that are left on the side. And all those numbers, they must be less than the locally largest here. In this picture, you have something that does this, and you may have numbers on the sides in this ideal. But then, and that's the key formula, and I just need 2 minutes from there. The key formula is, if you look at the locally largest exploration, and you look at anything that happens to, okay, let me denote those point process eta on the side. If you look at anything that depends on your locally largest exploration up to time t, provided that you're not dead at time t, things like that, then this actually is equal to the ideal model, the simple random walk model, started from P, the same F, same question you ask on the S eta as well, restricted to 0t. And here the only condition is that it is a locally largest exploration. What does that mean? Being a locally times, okay, H transformation. Tilde is just here to mean that I remove the exponential factor. Being a locally largest exploration is that actually none of these points that I've left on the side is larger than my current exploration. So if I restrict to this, if I restrict on this model to those explorations where all the points on the side stay below my curve, then I have a locally largest exploration, and that's the same here. I just have this factor here, but this factor here is really easy to interpret once you look at the formula. And now here is the crux.
So we can, we are close to conclusion.
10 seconds.
Okay.
20. Okay, once you have the key formula, allez, 30.
31.
Once you have the key formula, you take f is equal to 1, you get 1, and you pass this guy to the limit. Because this process is just more or less a random walk. And so when you pass it to the limit, you have a random walk. And you have the jumps of this random walk. And the jumps of this random walk are actually the guys on the side in the limit. And this random walk in the limit converges towards the beta stable Levy process. And the beta is the guy that I erased. It's the exponent that we didn't know. This exponent for the WP. It's a beta stable Levy process. And when you pass it to the limit times up psi t of psi 0 to the minus beta. So you get 1 is equal to the probability that a beta stable Levy process started from 1. If you look at all its jumps up to time t, and all its jumps are below the current curve times this. That's a beta stable Levy process, and that's the Levy process with beta. So that's actually, you can compute, and that's a function of beta. But this function of beta should be equal to 1. Lovely function involving hypergeometric beta function, but there are only 2 solutions, beta 3/2 and beta 5/2. Here is the 5/2. Voilà. Thanks.
Thank you very much. So I propose we take a small break before the next talk in 10 minutes essentially, and we can keep discussing further over. I mean, in these 10 minutes. Thank you.
Sorry for going off.
No, it's okay. It's okay. Okay. So thanks again.